AI benchmarks look like an objective measure of progress, but in practice they increasingly show something very different from the real capabilities of models. What we see in leaderboards and result tables is the outcome of an entire chain of decisions. How the test data was selected, which metrics were used, in what environment the evaluation was run, and what assumptions were made in advance. As a result, two models with very similar scores can behave in completely different ways in real-world use. Benchmarks, therefore, do not measure model intelligence, but how well a model fits a specific test. In this presentation, we will show why this leads to a false sense of progress and how four main mechanisms, data quality, overfitting to tests, inconsistent metrics, and the gap between lab and production, systematically distort our view of what AI can really do. AI benchmarks follow exactly the same rule as classical information systems. Garbage in, garbage out. If inconsistent, biased, or noisy data is used for testing, even the best model will produce misleading results. The lack of standardization of test sets means that different benchmarks measure different things, even when they use the same names and metrics. Biased samples favor specific types of answers, while noisy tests introduce randomness that destroys comparability. In such a situation, a high score does not mean a high-quality model. It only means that the model adapted well to flawed input. Garbage in leads to garbage out, and entire leaderboards become a measure of data quality rather than of the true intelligence of models. This reveals one of the most destructive mechanisms in modern AI: training for the leaderboard instead of for real understanding. When a benchmark becomes the goal itself, models start memorizing test patterns instead of learning general rules. They are then optimized for specific metrics, just like the archer in the image aiming at the benchmark target rather than at the real problem. The result looks like intelligence, high scores, records, and media headlines. But this is artificial intelligence in appearance only. A model that scores 95% on a leaderboard may completely fail in new, unseen situations. Benchmarks reward fitting the test, not the ability to generalize. High scores increasingly reflect mastery of the ranking game, not of solving real problems. The lack of standardization in AI benchmarks means that in practice, no one is measuring the same thing. Different teams use different tokenizers, different metrics, and different evaluation scripts, and each of these choices can shift results by several, sometimes even dozens of %. This means that two models tested on the same benchmark were often evaluated under completely different conditions. Some use BLEU, others ROUGE, others exact match, and still others apply custom heuristics. On top of that come differences in pre-processing, random seeds, and library versions. The leaderboard stops being an objective measure of progress and becomes a collection of incomparable numbers. When everyone uses a different ruler, you cannot know who is actually better, only guess. AI benchmarks often assume that a model score is an objective property of the model. In reality, it is not. The same model run on a different GPU with a different library version or with slightly changed configuration can achieve significantly different results. Differences between CPU and GPU, CUDA versions, PyTorch or TensorFlow builds, and numerical precision settings introduce variability that is sometimes larger than the difference between competing models. If one team tests in a heavily optimized environment and another in a default one, comparison becomes an illusion. Without containerization, version pinning, and identical configurations, a benchmark measures the setup, not the model. That is why leaderboard results often fail to translate into real deployments. AI benchmarks are designed in laboratory conditions, clean data, narrow tasks, and fully controlled environments. Under these conditions, models achieve impressive scores because they do not have to deal with the chaos of the real world. In real systems, everything is different. Data is incomplete, contradictory, and constantly changing. Tasks require multiple steps. Users behave unpredictably. A model that performs well on synthetic tests may fail when it must combine context, memory, and decisions in real time. This is why high benchmark scores often do not translate into production usefulness. Tests measure narrow skills in a sterile environment, not the ability to operate in real, messy processes. One of the biggest mistakes in AI benchmarking is trying to reduce very different systems to a single number on one leaderboard. Language models, vision systems, and decision-making agents solve completely different problems. Some generate text, others recognize images, others plan and act in dynamic environments. Each requires different test data, different metrics, and different success criteria. When they are compared with one score, a false hierarchy is created that says more about the test design than about the real capabilities of the systems. The leaderboard becomes a simplified ranking that ignores usage context, error costs, and real business value. One number cannot describe such complex systems. High benchmark scores often look like an objective measure of AI intelligence, but in practice they are largely a product of how the tests were constructed. Models can be overfitted to specific test sets, memorizing patterns instead of truly understanding problems. Data leakage is also common when parts of test sets end up in training data, artificially inflating results. An even bigger issue is missing context. One number tells you nothing about model stability, the cost of mistakes, or how it behaves in real scenarios. A leaderboard shows ranking, not usefulness. That is why a single score is never enough to decide whether AI is actually fit for work outside the lab. Thanks for watching. If this was useful, consider subscribing for more technical, no-hype analysis of AI and technology.